Alright, let's talk about the stable matching problem. I'm first going to go over an example of my own creation, and then we'll talk about the actual original problem. Alright, so here is a setup. For this stable matching problem, we have a goal, right? Given n people and n weapons, we want to find a suitable matching. So, in this problem, both groups will rate the other group with a preference from best to worst. So what I mean by that is, right, we have n people. In this case, n is 3. So we have 3 people, 3 martial artists, and we have 3 weapons. Alright, so of course, with the martial artists, they have a preference of which weapon they like the best, right? So they'll rank it from best to worst. And with the weapons, this is a fantasy setup, right? So the weapons also have a so-called preference of which people they like, right? It's kind of like Thor's hammer, right? You can only wield it if you are considered worthy. And, maybe some people, they have like more energy or more intelligence or just anything like that. But for whatever reason, these weapons have a preference of which people they prefer. And of course, with the martial artists, maybe they would prefer using an axe over a bow. So in any case, both sides have their own preferences of which pair they would like. Alright, so given this setup, let's say this is the preference of each group. So for example, given our guy X right here, his first preference, right, which weapon he wants the most, is the axe. In second place, he wants to wield the bow. And he really does not want to wield the club. Similarly, for Y, he really wants to wield the bow. And he's okay with wielding the axe. And he does not want to wield the club. And lastly, for Z, she wants to wield the axe. She's okay with wielding the bow, and she does not want to wield the club. Alright, and for the weapons, they also have their own preferences, which martial artist, which person they would prefer to be their wielder. For our axe, it really likes Y, right? It wants to get paired with Y. Maybe Y is the tallest, or maybe Y has the most upper body strength, or, Y has the most spiritual energy, etc. It is okay with letting X wield it, and it does not want Z to wield it. And so on and so forth with the rest of the weapons. Alright, let's talk some definitions. So, a perfect matching, in this case, just means each person gets one weapon and each weapon gets one person. In other words, it just means a one-to-one relation, right? It doesn't really matter who is paired with who, so long as each person and each weapon has an exact pair like so. Stability means there's no incentive for some pair to undermine the assignment by joint action. Alright, it's kind of a mouthful. Basically, stability means each person is okay enough with their pairing that they won't be like, actually, no, I don't like this, I want it out. So let's give an example here. A pairing is unstable if the weapon and the martial artist prefer each other to their current partners. So what this means is, alright, let's say we have Y and the club wielded together here. And then we have Z and the axe, right? Let's say Z wants to wield the club and Y wants to wield the axe. And let's say the axe prefers Y and the club prefers Z. So in this case, we clearly have this kind of relationship where they prefer each other than their actual pairs and their actual partners. So they would obviously want to break this assignment and kind of run off with each other like this, right? In other words, there is incentive for them to undermine this assignment by joint action, which means, they run off together. La 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 la. So, that means these two pairings, right? This is an unstable pair, and this is an unstable pair. It's like a little bit weird, but basically it does not mean like this is an unstable pair. It means this and this is an unstable pair. In other words, the unstable pair, P and W, can improve by ditching their current partners. So what we mean by stable matching is we have a perfect matching with no unstable pairs. Now, this will definitely make a lot more sense after we start getting into the example. Like the first time I saw this, I was like, what are you talking about? So I think it makes a lot more sense after we actually see the example. And therefore, the stable matching problem is, given the preference lists of n martial artists and n weapons, we want to find a stable matching if one exists. So, okay, this is the example on my prof slides, but if you really want to be pedantic, you can actually cross out the if one exists, because in the algorithm we'll see later on, there is a proof that shows that the algorithm will definitely find a stable matching. So yeah, if you really want to be pedantic, you can like cover up this part. All right, let's go back to this example. All right, so we have the preference lists. Now looking at this, can we assign a match between these two groups such that it is a stable matching? So right now we don't really have an algorithm, so we kind of just like want to stare at it and see like, okay, can we think of something, right? All right, let's try this. What if we match X with C? What if we match Y with B? And we match Z with A. Is this a stable matching? Oops, I guess I'll do this. And the answer is no, right? Now, just because two people prefer each other the least, or I should say, just because a martial artist and a weapon prefer each other the least, does not mean they are automatically an unstable pair, right? It doesn't like mess up the entire thing just because they dislike each other. Because if they don't have an option where there's a weapon or a person that prefers them more than their current, condition or their current circumstance, that just means it's still stable either way, right? Like maybe both of them are just like, you know what? We can just make do with this situation. All right, let's look at X and C. So you can see from here that X does not like C at all, right? Again, right, this could be possibly stable if X doesn't have any better choices than C. Maybe he just has to make do with C, with the club. So X is not very happy in this situation. Now let's look at the club, right? The club really likes X, so the club is very happy with this setting, with this arrangement. All right, let's look at Y. Now Y has the bow, and Y really likes the bow, so Y is like, yippee! Y is very happy with this arrangement. And the bow is okay with Y, so the bow doesn't really mind either. And lastly, Z is also very happy with the arrangement. Z really wants to use the axe. And the axe is unhappy. All right, so in this case, we can see that, right, look, the axe prefers X over Z. And X prefers the axe over the club. So even though these two are already paired up, X could be like, wow, I see the axe. Because, the axe is X's preferred weapon. So X will take the axe and run away. That means these two are an unstable pair in this. So it will break the current arrangement. This is not a stable matching. All right, what about this kind of matching? What if we pair X with the axe? We pair Y with the bow, and we pair Z with the club. Let's see if this matching is stable or not. So first of all, we can see that X is very happy with the axe, and the axe is not terribly unhappy with X. We can see that for Y, he is very happy with the bow, and the bow is not terribly unhappy either. And Z, she does not want the club, and the club does not want her either. But you know what? We can make do, right? So let's see if this pairing, this arrangement is stable. So although Z and the club really don't like each other, they don't really have a choice either way, right? So these two are happy and they can make do with this arrangement. And for Y and X, they are very happy because they got the weapon they wanted. And for the axe and the bow, even though they are not matched with their preferred martial artist, they're still okay with it, right? They're like, you know what? Because these two will not run off together because, X likes the axe. And these two will not run off with each other because Y likes the bow. Therefore, this arrangement is a stable matching. All right, so to reiterate, a stable matching is basically you want to pair all of them such that there are no unstable pairs. Unstable pairs meaning they'll run off together with each other. So that is my, funky little example. But the actual original problem is as follows, right? In 1962, two dudes named David Gale and Lloyd Shapley were looking at this problem. They're like, okay, given college admissions, right? Given colleges and they want to accept students, or, given a lot of companies and they want to recruit employees, how can we assign all these arrangements such that everybody is happy and, there is no case where there's, for example, a company who prefers another employee, over the one they hired, and then the employee in question prefers this company over the company they're actually working for, right? Or, in the college situation, right? How do we prevent the case where one college has a student that is not attending that college, that they prefer the other student over the student they currently have, and the student in question also prefers that college over the college they are attending. So even though these two devised an algorithm, this problem was actually already existent before they came along, right? For about a decade earlier, there was already the med school resident issue where they were also trying to figure out, how do we assign med students to residencies and hospitals and whatnot, right? So in any case, the goal is, given a set of preferences among hospitals and medical school students, design a self-reinforcing admissions process. And what does self-reinforcing means, right? Self-reinforcing just means there is feedback provided within this the system itself, and it'll give a natural and desirable outcome. So basically, it's saying if you follow the rules right, individual self-interest will prevent deals from being made behind the scenes, right? It's saying that how can we design a system such that with the given feedback, there won't be any pairs being like, haha, let's run off, psych. Everybody will just follow the system and just naturally end up with an outcome that is desirable. So, in the next one, we'll talk about some algorithms, actually, an algorithm that will solve the stable matching problem, right? Because for this one, we literally just looked at it and we're like, how do we solve this, right? And because there's only, n is equal to 3, right? We only have 6 elements in total. We can pretty easily, even just brute force it. But in the real world, things are really complicated, so we want to have some way of algorithmically figuring this out. Thanks for watching, and see you in the next one.